Whenever you pass an electric current through a wire, as I said earlier, there is a voltage drop across the wire, and electric energy is converted to heat. And this is where I say IV. What is I? I is your amps, and that's actually measured as an A, or a coulomb per second, as I showed you earlier, for those who are astute at their physics 2. And your volts are V, and we measure that in volts. And so when we multiply those two together, like I said earlier, we get power. And delta E is the amount of energy converted from one form to another. So if I go back up here, we're taking electrical energy and we're converting it into thermal energy, otherwise passing off as the flow of thermal energy as heat. Delta T is the duration of which the conversion takes place, as I mentioned earlier. I is the current, V is the voltage, and so your real equation right here is IV delta T. So that's your amps times your voltage times however long you ran your power supply. So, anywho, it's a really handy way of actually figuring out how much energy you put in the system, and for heat and temperature, I really like it. It does have some drawbacks. When you run an electric current through water, it's generally not the you don't want to drink the water while it's doing that. Yeah, it's definitely pretty. And 12 amps, 10 amps, I'm sorry, is a lot. So there is some caution in it, but as long as people are safe, it doesn't really cause any issue. And no one's killed themselves yet, so I'll take that as a plus. So yeah, at least not with respect to this. First set of experiments. From your graphs, you see that for an object, in this case 100 grams of water, there should be a linear relationship between energy and added temperature. The slope of this line means something, and it's called heat capacity. And so when you have this little line here, this is energy versus temperature, and I'm going to draw the best line you've ever seen today. And you notice that your units for heat capacity is going to be a joule per degree Celsius. Heat capacity tells you how much energy you need of a certain amount of massive substance, how much energy you need to move it up or down 1 degree Celsius. This is heat capacity. Most books will call it a K. I believe it's stretching my brain. Sometimes you'll see it as a capital C in certain chemistry books. I call it a K. Why do I call it a K? Because as we'll get into later, there's specific heat capacity and regular heat capacity. And if they're both C's, that looks kind of funny, especially if one's capital and one's not, because then you're going to get them confused. So I switched a long time ago to a K, and well, no one's complained, so we're going to go with that. So what about for 100 grams of water? Well, the slope of the graph shows that for 100 grams of water, it's 418 joules degrees Celsius. That means you need 418 joules of energy that need to be added to move 100 grams of water to change its temperature by 1, either up if you want to put it in, the energy in, or down if you want to take the energy away. And so when you found that slope, whoopsie, you'll see that it's 418. Analyzing graphs, and I better have fixed this. Notice that even though the mass of the water is increased in each experiment, the data still has a linear relationship. So you should get very similar values, 209, 313, 418, etc., etc. For each mass is going to have a different heat capacity. So note that each mass has its own unique write the word has, there you go. It is, oh wow, English for me, English. Its own heat capacity, there we go. So each one has its own capacity, and every mass will have its own individual heat capacity. How is that useful? Well, it is a quick and dirty way sometimes if you don't actually know the specific heat of the material. But if you do, as we'll get in earlier, it's kind of not as well used, I think. From our data, we see that as mass increases, then the heat capacity does as well. And we can find a relationship between the heat capacity and mass. And that's called the specific heat, as I mentioned earlier. This is actually called the specific heat capacity. I will simply call it the specific heat. And why is that? Because Normally, if we're in a lab, and sometimes we would do back and forth between heat capacity and specific heat capacity. If I tell you specific heat capacity, and it's happened before, you might not hear the specific heat or the specific part in front of the heat, and you just hear heat capacity, since 2 out of the 3 words are exactly the same. So instead, I just simply call it specific heat, and then heat capacity. Only one word is used in between the two. It causes a lot less confusion. If you end up teaching some sort of chemistry or physics, and you have to do this, and I have, just call one heat capacity and the other one specific heat. It'll make your life easier. A little life lesson there. So the slope of the heat capacity versus temperature is going to yield the specific heat. So basically what we did was we took all of our heat capacities, and I spelled it correctly, there I go, and we graphed them on the y-axis versus the actual mass, and then when we found the slope, we got 4.18. This is what's called the specific heat of water. It takes 4.18 joules to heat up 1 gram of water 1 degree Celsius. The unique thing about specific heat is it's true for all of the substance. So this is true for all water. Now you're saying, well, what if the water has, different properties? It's heavier water or lighter water. I don't know. It has more minerals in it or something. Yeah, it does have a little bit of a change, but for the most part, we're going to be dealing with standard conditions. We're dealing with distilled water, so you can think of it as 4.18. Some places do 4.186. Not sure why the book or whoever wrote this curriculum a long time ago did 4.18, but I've stuck with it, and it's close enough. Some places will do 4.180. It just kind of depends on your initial conditions, I suppose, but we'll use 4.18 from here on out. Every material is going to have its own specific heat. So water is 4.18, but iron is going to be... Okay, let me not talk about this. Let me go here. It moved away. I'm sorry. Iron is 0.46. Your aluminum is 0.88. Lead is 0.13. So let me do something here I've never done before, but maybe I shouldn't because I'm kind of regretting trying something new already. Let's see here. Yeah, I can color iron. Oh, look at that. There we go. Let's do aluminum. Color. Look at me color. And then, let's do some lead because lead is cool. Is lead cool? No, not if you eat it. Don't eat lead. Okay, why did I do that? Well, because notice that these are all metals. Oh, let's make a key. Oh, we need a key. Yes, we need a key. Metals. And I like metal. Okay, so notice one thing about all your metals. They have very low specific heats. These are known as good conductors. Your metals are good conductors. A good conductor is not, basically they allow heat or electricity, energy or electricity to transfer through relatively easily. They have very low specific heats because it doesn't take a lot of energy to heat them up or cool them down. Then let's do some red highlighting. Your water, that's not red, that's yellow, you said. And I know, I'm aware of that. So we're going to change it to red. And there. That doesn't look too good, but it works. So your waters, your oils of the world, ice, alcohol. And there we go. Alcohol, all that good stuff. Going back to there. These are your insulators, and I need to be black. There we go. These are your insulators. Your insulators generally take a lot of energy to heat up or cool down. Water is particularly a good insulator. A good example would be, let's say I want to boil some eggs because I'm hungry. Alright, so I get out this big old, let's call it an iron pot, and I fill it with water. And after about, 7 minutes, I touch the iron pot, it burns my hand. But if I touch the water, it doesn't burn me at all. That's because the iron just heats up so much better. It's a good conductor. And so it's able to heat up faster than the water. Even though both could be exposed to the exact same amount of energy, well, let's assume they are, it doesn't matter